Hi, thanks for coming by to learn more about my poster. If you've already watched the brief overview I gave to the SMB organizers, then this will be a little bit of a recap, and I'm sorry about that. But my name's Amanda Lobmeyer. I'm a faculty member in the math department at Texas Tech University, and this work has been done in collaboration with John Banks, an entomologist at Cal State Monterey Bay. What I'm going to do is just sort of talk you through the poster the same way I would during an in-person poster session, in case I can't talk with you one-on-one during the SMB poster session. But you won't be able to ask me any questions, so if you have any, please feel free to reach out to me. My email is on the poster, and I'll also be available via Sococo, and I'm really happy to exchange ideas with anyone. The motivation behind this project has been to look at the potential for the biological control of an agricultural pest by a community of its natural predators. The pest I tend to think about is an aphid, which is a really common pest that can reduce crop quality and also transmit plant viruses. And then the community of predators would be sort of the beetles and spiders that naturally reside in agricultural fields. And in this project, I'm thinking about how the composition of those fields affects predator behavior and efficiency as biological control agents. So there's a lot of different aspects of field composition. The size of the field, whether it's very large or very small, affects the speed with which predators can move throughout the field. And kind of the way that people manage the edges of their fields, they might clear cut them or permit weeds to grow up around there, can affect predator movement into the fields during the season. And then at the landscape level, which most managers won't really be able to control, you have the idea that everything that's around the field affects the community of predators that can move within the field. And because we were thinking about these spatial problems, my collaborator was really interested in how pesticides might kind of play along with these ideas. So usually, natural predator communities work alongside conventional pesticide sprays in something called integrated pest management. And those sprays don't need to kill the predators in order to have negative effects on them. So these negative effects we call sublethal because they don't kill the predator. But what can happen is when a predator is sprayed by a pesticide, it might become disoriented, kind of just move around aimlessly, or sluggish and just move around more slowly. And both of those things affect the efficiency with which the predator moves around a field, particularly at large scales, and can identify aphid pests to consume. So we formulated a partial differential equation model to describe the different behaviors that we think will happen in these fields. And I'm going to talk through what's happening in the model, and then I'll sort of show you the equations if you want to look at them. So in this model, I'm really thinking about the interaction between two different populations. I have a pest, those aphids, or just a general pest if you want to think about it that way, and the predators, some community of beetles. Pest population can grow logistically within a single season, and it tends to diffuse aerially. What's happening there is that aphids have two modes of reproduction. One of them is asexual, very rapid on the plant that they're currently on, and one of them creates what's called a winged alate, sort of a different version of an aphid that can fly some short distance and then identify a new plant, kind of latch on and start reproducing there. And that aerial diffusion occurs when the aphids are really crowded and can also increase in the presence of predators because they tend to disturb aphids in the same way. And then the only loss to the pest population is due to predation by the predators. The predators don't grow within a single season, but what they're going to do is diffuse randomly through the field while foraging. That's just them walking around. And then when they're foraging, they might also exhibit directed movement towards their prey. So the beetles might detect that suitable prey is nearby, usually like by the type of like plant quality nearby. And then as they're moving in the direction of prey, intra-guild competition sort of between the predators might smooth out their movement. So they can't all move towards the abundant aphid areas together because they would bump into each other, compete for resources, kind of move around and return to their aimless motion. And then there's going to also be a term in our model that incorporates migration or release into the field. That just describes the predator behaviors normally. What I'm also going to implement are pesticide effects. And it's going to be a really simple sort of pesticide. I'll assume that there's some sort of threshold aphid density at which a pesticide is necessary. And then when that happens, the entire field is hit by the pesticide. 90% of aphids die immediately, and then predators suffer penalties to their diffusion and directed movement parameters. And the sort of purpose of this is that predators will become slower, they diffuse less, and then sort of more disoriented. They have less direction after the pesticide spray. And there they are. Model equations for this are given here. Maybe before SMB, I'll turn them into like actual teched up equations, but for now they just look like this. So I'm just gonna sort of show you the different components I talked about just now. The pest is a partial differential equation for single population A. It exhibits logistic growth, and then it has a diffusion parameter, that del dot del A. There's a baseline diffusion rate. That's just the aphids become crowded and they spread out. And there's also this additional diffusion rate, some constant times the sum of the predator communities. That's describing that idea that predators disturb the aphids and trigger their aerial diffusion to happen more frequently. And then the aphids suffer death due to being eaten by either type of predator community. The two predators are described by these equations right here for B and B sub S. B is just the general predator community. B sub S is the predator community which has been affected by sprays. So the predators diffuse, that's that random foraging they have, just del dot del B at some rate D sub B. And then they exhibit directed movement, that's prey taxis moving towards their pest that they like to eat with some velocity v, and I'll describe how that velocity develops later. And then there's just this flat migration rate into the field. We also can implement migration at the boundary conditions depending on the type of predator. B sub S is going to emerge whenever a pesticide spray happens. So some proportion of the predator community is affected by the spray and exhibits these dynamics. They're the same as for the regular predator community, except for that there's some pesticide penalty to their diffusion rate. And then the directed velocity for either the beetles or the beetles when they've been sprayed are going to be given by these equations here. And so what happens is the velocity sort of shifts to point towards directions where there are increasing pests. But then there's this other parameter that sort of smooths out the velocity so that when there's competition between predators, if the velocity tries to shift in one direction very strongly, then it spreads out a little bit more to describe the idea that all the beetles couldn't go one way. They would compete with each other and turn around. The sprayed predators have the same development of their velocity, except for, again, there is a penalty to the term corresponding to prey taxis, directed movement towards their pest. So the effects that we saw were kind of mixed. So we looked at comparing predator performance for pest control when there's a 90% penalty to their movement parameters compared to no penalty to their movement parameters. And we looked at differently sized fields because that's something I'm kind of interested in, between 5 to 200 hectares. That's a measure of field size. And so these figures right here along the horizontal axis describe predator diffusion, and along the vertical axis is going to be the percent reduction in pest control by a predator. So for increasing baseline predator speeds, you have more and more a reduction in their biological control when they're hit by this spray. And for different field levels, you can kind of see that behavior is different. Sort of for very small fields, you have this saturating relationship. The field is so small that at a certain point, the diffusion rate is sort of high enough to cover the field. And so the big takeaway there is that implementing a 90% penalty to predator movement parameters does reduce biological control. Sort of like you can reach up to a 50% increase in pest abundance or reduction in biological control when you have these mobility penalties. But we didn't get like the full result that I wanted to see. So I wanted to see some sort of interaction between that and your conventional pesticide sprays. But the the reason for the result that I'm about to show you is that when you need pesticide sprays in a field, it's going to be because the predator community is not very effective as a biological control agent. So any sort of penalty to the predator efficiency is just penalizing something that's already very bad. And so what we saw was that when we implement the predator penalties, we tried to look at whether you have to spray more frequently or whether the time between sprays has been reduced over a season. And so for different sized fields, the effect is different. But we see that the most difference is a few days. So compared to when there is no penalty to predator movement, a 90% penalty to predator movement just means that you have to spray your field 3 days earlier because there's 3 days of predator control you're missing out on, which isn't a whole lot on the scale of the season, which is like 60 to 90 days. And these effects can be kind of mixed across field scales and also the threshold at which you spray, whether you have a very high tolerance for the number of aphids, a low threshold level that you spray, or a very low tolerance for the number of aphids you like spray when they're at high abundances only. But those results are a little bit messy because kind of somehow the length of time between sprays is also affected by the number of sprays, which is going to change along field size as well as threshold level. So I'm still sort of disentangling those effects. Some ongoing work that we want to look into is sort of how the interactions just described in this poster are also going to be affected by other management strategies. So things like not tilling between seasons or building up banks for predators within a field or augmentative control when you dump a bunch of predators into a field. All those things kind of are feasible for managers and would affect the presence of predators in the field, like the abundance of them or the rate at which they move into the field. And then sort of long term, we'd be interested in looking at comparisons between our results and different types of models. One would be looking at a compartmental description where we think about that landscape mosaic and how there might be different fields next to each other. There could be movement between those fields or, natural like habitats breaking up those fields. And then we could also compare to sort of an individual-based description of how predators move within these fields and sort of see what happens. So at the bottom of the poster, I have a couple references, a prior paper where we just were developing this model, no paper yet where we have these pesticide sprays, it's still a work in progress, and a work that our model, actually the bones for this model for how to incorporate the directed prey taxes, that's the reference right there. So thank you so much for dropping by to learn about this project. If you have any questions, again, please do contact me.